Good morning. This video will demonstrate how one would employ the CAS registry, and in particular SciFinder, to identify seized drugs using data obtained from the NIST hybrid EI mass spec search. This current video is a resource that I'm using from another talk that I gave recently, entitled Approaches for Identifying New Psychoactive Substances, MPSs, at 2023 Current Trends in Seized Drug Analysis Symposium. And you can see that presentation on my website, A Little Mass Spec and Sailing. At the top, if you click on it, it'll open up and you'll find the presentation. But what I want to show you now is at the bottom. This is some excellent CAS training videos that I suggest that you utilize to learn how to use this very powerful SciFinder-n program. Here are the conclusions that we had in the presentation that led to the identification of this unknown. The hybrid search was critical in suggesting a PCP-related substructure. The molecular formula from accurate mass data was determined by DART. And we wanted to test SciFinder and the CAS registry as a much simpler approach than that shown in the presentation using chemistry. And I've also demonstrated this in a separate video on the website using ChemSpider. So you can see below, this is the substructure. If you take this phenyl and up to this nitrogen-containing ring here, there was something that occurred on this side of the ring, which was told to be the case by the EI NIST hybrid search, and showed that it was an angel dust, a PCP-related species. And it was ultimately identified in a much more complex approach using chemistry as the structure shown on the right, but now we'll demonstrate it with the CAS registry. We've opened up SciFinder-n in this window, and I'll start the video. I captured this while I was doing the search on SciFinder-n. So let's start it here. First thing I do is I go up to Substances in the menu. I type in the molecular formula, C21H29N, and then I go over and I draw the substructure we were talking about, the phenyl ring. And you'll notice as we go into this, I'm not real good at using this interface. You can actually import the structure if you wanted to from a drawing program you're familiar with, but I thought just to illustrate the SciFinder-n software, I would show you how to do it. So I've drawn the two substructure rings there. What I need to do now is block off all groups that I don't want to be substituted. I messed up here, so I did an undo. And I'm putting hydrogens at every place that I don't want any connections to occur, because the hybrid search within the NIST software showed that this part of the ring was there and there was nothing branched off that part. The only branching occurred was on the central CH2. I put a nitrogen in the ring there, finish off the other hydrogens on the aromatic ring just to show that there's no attachment at that point. So the only place now that we can attach is at the CH2. So we go back, we've got our substructure now, we'll do the search where we'll search the molecular formula and we'll require it that it has that substructure and see what results we get. And you see you have two results that came up, and both of those results are the ones we got from the chemistry, and the one at the top is the desired structure, and the one at the bottom was the other second structure. There are actually three, but these are two of the three that I'd proposed, and as I said before, the top one is the correct one. So you can see this is a much easier approach. If you look at the presentation, we used a lot of chemistry. This is much more directly easier to do. And I also did the same thing in ChemSpider and get similar results. So you could do it either way. You've got to remember that CAS is a fee-based, you pay for it, and ChemSpider is free. We'll now try another compound that we identified in the presentation using SciFinder. So the first thing is that the hybrid search showed a substructure and a presence of a carbamate group by mass spec and infrared. A molecular formula of C14H20N2O2 from the hybrid data was indicated. This was such good data because you don't really need accurate mass data in this case. Such a simple delta mass of 16 pointed to the presence of oxygen, and then the substructure and the functional group indicated the molecular formula that we will use within the SciFinder search. The IR and mass spectral data matched that obtained for another laboratory and our proposed structure in the presentation. You can see it below. It had a molecular weight of 248. It is an ethyl carbamate. So we wanted to try SciFinder. Let's just say that we didn't find another match for it, and we thought that we needed some additional candidate structures. Could we do that within SciFinder? And that's what we will be talking about in the next few slides. And what will it be? Well, I'm looking to see if maybe there was some modifications in this part of the compound right here. I know the carbamate's out there, so I wanted to see if this had been rearranged in some different manner, but still having the same molecular formula and molecular weight. We did the same thing in ChemSpider and got some interesting possibilities there. And as I will remind you before, that ChemSpider is free and SciFinder has a fee associated. It costs money. And ChemSpider has many fewer compounds, and also SciFinder has many more compounds. So, and is also highly curated. So I go back and forth between both of the applications and sometimes find complementary data that's useful. Now I'll show you this SciFinder session for this compound. We'll start I pre-recorded this, so I'll start the video. You can see the first thing we're going to do is put in the molecular formula for the compound. So we've added it. We'll go up to the drawing program and put in the structure. As I showed you before, it's a little hard for me to deal with this. So a lot of times I'll import the structure. So I'm going to import it as a mol file that we used in some drawing program. So we're going to upload the structure, choose the file. We're going to go pick it and open it. You notice when we open the file that all of the sites that I wanted to block from having any connection are attached hydrogens in it. So I've allowed only no branching in those for the exact or the substructure, and now we'll search limiting those with that structure with the molecular formula. You see when it comes up that this program does the structure match as drawn, found 1. You can see it right here. It does the substructure as 1, but it also shows similar structures by a Tanimoto-like search, 2,898. And that's the one we want to use because we're looking for similar structures and not the exact one. And if you scroll through these, you can decide what level you want to look at. I'm going to look at 13 of them, which is 85% probability and above. And we'll just take a look through them and see if we had any other possibilities that might spur some thought about the possible identity of the compound if we hadn't have known what it was from the data, just to get other ideas of how it might and how it compares to the fragmentation we observe in the EI mass spectrum of the compound. So that's pretty much it. I just wanted to show you how that compared to the ChemSpider one that I've done before, so you can take a look at the other resource video to see how that compared, but both of them do Tanimoto searches. Other parameters can be used to search SciFinder that might be useful in identifying unknowns, such as keywords, key phrases, and the other thing that they added in recent years is molecular weight. So I wanted to talk a little bit about how they calculate molecular weight. The molecular weight used exclusively in SciFinder, that's one type of molecular weight, but ChemSpider uses monoisotopic, nominal, and molecular weight. And that's a little bit unfortunate that SciFinder uses only molecular weight because it's probably the least easy to use and the data system really doesn't give you that value, while nominal and molecular weight are more easily calculated by most mass spec data systems. Molecular weight is calculated using the average molecular weight of the nuclides, thus those present in the periodic table, typically used by chemists to calculate molar ratios for reactions. And that's probably where it comes from. Really, SciFinder and CS Registry was developed for chemists, and chemists really like the molar ratios of the molecular weight for calculating reactions to how much to react together. Nominal mass is calculated using the mass number of the most abundant isotope of each atom without regard for the mass defect. All molecular ions and fragment ions are corrected at nominal mass when imported into the NIST search program. In most cases, it can do accurate mass, but most of you, if you use quadrupoles, you would be using the nominal mass. So it always rounds it off, chops off everything to the right of the decimal. The monoisotopic mass you'll often have in your data systems, even for a quadrupole, is calculated by taking the sum of the accurate masses, including the mass defect of the most abundant naturally occurring stable isotope of each atom in the molecule. And that just depends on the accuracy. You could have 1 digit for a lot of quadrupoles to the right of the decimal, some 2, and some up to 5 in some of the new accurate mass instruments. So let's look at the data for octyl stearate here, C20H56O2. It has a molecular weight, which is the chemist's molecular weight, of 396.690. This is the largest of the three. 396 is, of course, the nominal. It's been rounded off to 396 even, nothing to the right of the decimal. And the monoisotopic mass is usually what the data system gives to 1, 2, 3, 4, 5 digits here, but sometimes 1 or 2 would be rounded down to 396 to the nominal mass that's observed. So if you're going to use this, you need to be aware on how to calculate it. Well, you can calculate the molecular weight for mass spec data, but it's not easy to do. It's not easy to determine by mass spec using most data systems. None that I've used would have to normalize the isotopic data and mass to charge values to one or more places to the right side of the decimal, and also know the standard deviation for the measurement when you put it into the system, because you always have error bars around it, so you don't leave something out. You have to take what you think it is and put a little error to the left and to the right. And if you want to see more about, you can see the paper that we wrote in the journal article at the following link, and this is one of the figures from it. And bottom line, it's just not very practical to do. So what's the relationship of the species present to the molecular weight observed? Well, carbon and hydrogen increase the molecular weight the most. If you see the graph below, the incremental mass increase for a series of a hydrocarbon, you can see from methane on up to about a hydrocarbon having a molecular weight of 700, it increases it up over to 1.4 over that range. But a lot of the places that you would be interested in, maybe in the 200 to 400, it's going to be about 0.6 to 0.8 increase. Sulfur, oxygen, nitrogen, fluorine, silicon, iodine, etc. don't change significantly this value due to their value or the number of these elements typically present in a compound in most cases. Chlorine and bromine can have a significant effect, especially as the number present increases in the molecules. So you need to be more careful when you have those present. So I hope this has been useful to give you an idea of how you might try to calculate molecular weight, but just be cautious and leave the error bars such that you can find what you're looking for and you don't exclude something. So I hope this video has been useful to you, and also the resource video for Kim Spider for doing these same two model compounds for comparison. And remember again, SciFinder has a fee. It costs money to do, while Kim Spider is free. But Kim Spider has fewer structures in it, and it's not as highly curated, and you can't search by keyword. So, but there are some advantages with respect to monoisotopic molecular weight searches. So I hope again that all this has been useful to you, and good day.